It's been a long day, and I'm really tired right now, so tonight's going to be a bit of a short one. Sorry, but I refused to not study because I felt as if it was going to be more dangerous than just studying a little bit. Plus, I have another calc midterm that's on Friday, so I'm going to need as much review as I can possibly stomach. With that, let's get started on the new stuff. This is going to be on the midterm, so I need to make sure that I know it. When we're talking about partial derivatives, we know that both of these represent the change in z along a certain path. With the case of the partial derivative with respect to y, it is along the y-axis. But what if we wanted to take the partial derivative with respect to an arbitrary path? Let us first say that we are given some function f of x comma y, and we are asked to take the derivative with respect to a path that is represented by this vector v. I just randomly chose numbers for x and y. Once you boil past all the theorem, this is actually pretty easy to do. Let us say that the magnitude of some unit vector u is 1, and that this unit vector is acting in the same direction as v. What we want to find is the directional derivative with respect to u. This, my friends, is going to give us the derivative with a path along the vector, which is pretty cool. For this, we are going to need to reintroduce some old topics. The gradient vector, which we recall as being f partial x comma f partial y. By reintroducing the gradient vector, we can find the equation for the directional derivative along this particular path. It is simply going to be the gradient vector dotted with u, our unit vector, in the direction of the original vector that we were given. Pretty simple enough. I've already extensively gone over how to find dot products, so I'm not going to spend my time on that. Lastly, for any given level curve, the gradient vector is going to give you the direction of fastest increase for a point on that level curve. Next comes maxima and minima on multivariable functions. We know that on two-dimensional functions, we can have local maxima and minima and absolute maxima and minima. On multivariables, you can have the same thing. It just is, as always, more complicated, but not that much more complicated. And I don't believe that we're going to be covering absolute maxima and minima on the midterm on Friday, so I'm just going to very quickly go over the introduction to it all. Let's get started. First, let us imagine that we have some completely continuous multivariable function, f of x comma y. In two dimensions, we know that critical points occur at either endpoints or places where the derivative is 0 or undefined. With multivariable functions, it's kind of like that. Instead, whenever grad f is equal to a 0 vector, we have a critical point, or f is not differentiable. Since grad f is equal to the partial derivative with respect to x, comma, the partial derivative with respect to y, and since this thing needs to be equal to a 0 vector, which is of course 0, 0, we know that wherever this system of equations has a solution, there's going to be a critical point, meaning that we are going to need to solve for our critical points, which is a bit of a pain, but not too bad. Next, let us imagine that we have found all of our critical points, and we want to find out if it is a local maxima, a local minima, or a saddle. I'm not quite sure what a saddle point is still yet, but I'll go over it tomorrow. I'm too tired for stuff tonight. To find out this information, we need to use the second derivative test. Much like how there was a second derivative test in two dimensions to find whether something was a maxima or a minima, there is a second derivative test in three dimensions, which is the following. For the point we want to test, the number d is going to be equal to the partial derivative with respect to xx times the partial derivative with respect to yy minus the partial derivative with respect to xy, the quantity squared. This is going to be something that I put on my note card. These are just second partial derivatives. The first letter tells you which to take the partial derivative with respect to first, and the second tells you which to take second. After we have found our values for d, there are a couple of situations that need to be fulfilled. If d is greater than 0 and the partial derivative with respect to x is greater than 0, then we have a minimum. And remember, we're plugging in the point we want to test. If d is greater than 0, but the partial derivative with respect to x is less than 0, then we have a local maximum. Lastly, we know that if d is less than 0, we don't need to know the value for the partial derivative of f with respect to x, because if d is less than 0, we know we have a saddle point that we're dealing with. I think that's going on the note card. I don't want to have to memorize this. This I think I could do, but not this, which is strange. I don't know why. But oh my god, Lord. After how poorly the past midterm went in calculus, I'm not excited for this Friday. Despite all of my other midterms going relatively spectacularly well, I really don't want this midterm to ruin the streak, which is, I guess, why I'm trying to, study so hard for it. But despite me having, physics and statics today also, they were relatively complicated topics, and I think I would actually be doing myself a disservice by trying to study them when I am this exhausted. I wouldn't learn well, I would get frustrated, and I wouldn't want to revisit the topics, which would hamstring my preparation for future midterms, especially because we are actually starting to learn sort of the building blocks for new entire topics in both of these classes. As a preview, in statics today we learned about centroids and center of masses. As a preview, in statics today we learned about centroids and centers of masses. And in physics we started to learn about resistance and Ohm's law. Two topics that are really quite vital for the class. I have a midterm on this stuff this week. This is the vital stuff. Everything else can sort of just wait for a little while. Especially because I have a quiz on the stuff I just showed y'all tomorrow. I wish the homework was due before the quiz so I could force myself to practice. But complaining will have to wait. I don't have time for it. It can happen next week when my midterm's done. But in the meantime, I hope y'all have a great day or evening or whatever time it is where you are, and I'll see y'all tomorrow.